Greetings, parasite ecologists. In this video, I want to go over a few important terms that you're going to need as you dive deeper into the world of parasite ecology. This list contains 23 terms that you should understand before you move forward in the videos. Being able to define and use these terms is going to enrich your understanding of future videos and help keep us all on the same page. Please pause the video to give yourself time to create your own glossary of these terms with definitions in your own words. You can use 3 resources to help you. The Foundations of Parasitology textbook by Larry Roberts and John Genovi, a paper by Albert Bush and colleagues entitled Parasitology Meets Ecology on Its Own Terms, and a paper by Kevin Lafferty and colleagues entitled Trophic Strategies, Animal Diversity, and Body Size. You'll find the links to all 3 resources in the video description below. After you finish building your glossary, you can continue the video and we'll go over a few key terms together. Pause the video now. Welcome back. There are a few terms that I really want to go over to make sure that we have our definitions straight. First up, disease. A disease is a deviation from the normal structure or function of an organism, which results in a fitness cost. Now, there are communicable and non-communicable diseases. Heart disease occurs when your heart doesn't have its normal, healthy function, resulting in a fitness cost. But heart disease is not communicable. In these videos, we'll be talking about communicable diseases, where the presence of a parasite causes a deviation from the normal structure or function of a host and results in a fitness cost to that host. For example, the parasite Schistosoma mansoни causes the disease schistosomiasis. The parasite Plasmodium falciparum causes the disease malaria. And the parasite Wuchereria bancrofti causes the disease lymphatic filariasis. As you are building your glossary, you read in the paper by Kevin Lafferty and colleagues about the difference between microparasites and macroparasites. Now, when you first started reading, maybe you imagined that macroparasites would be big parasites like worms and arthropods, and microparasites would be small parasites like viruses and bacteria. But the definition is actually a little bit more nuanced than that. A macroparasite is a parasite with intensity-dependent pathology. And a microparasite is a parasite with intensity-independent pathology. What do I mean by intensity-dependent pathology? Well, imagine that you're colonized by a single parasite. Is the fitness cost less than it would be if you were colonized by many parasites of that same species? If the answer is yes, you're dealing with a macroparasite because the pathology that you are suffering is dependent on the intensity of infection. More parasites, more problems. If the answer is no, then you're dealing with a microparasite because the pathology that you're suffering doesn't depend on the number of parasites that colonized you. Consider, for example, this poor moose infected with ticks. Imagine that this moose is walking around the forest and it picks up a single tick. That one tick will cause a negligible fitness cost for this moose. Now imagine that the moose picks up 1,000 ticks. At that intensity of infection, the moose will lose a lot of blood and a lot of energy that it could otherwise have put toward doing moose things like growing bigger or making babies. In other words, the pathology of infection is intensity dependent. And that makes the tick a macroparasite. On the other hand, consider the malaria parasite. The malaria parasite is super sneaky. Once it's injected into its vertebrate host by a mosquito, it replicates inside the host body, creating millions upon millions of copies of itself. Doesn't really matter whether one parasite is injected or 1,000, you're going to get full-blown malaria either way. In other words, the pathology of infection is intensity independent, and that makes the malaria parasite a microparasite. You're probably familiar with plenty of microparasites. Think common cold, COVID-19, rabies virus. You can be infected with one little rabies virion, or you can be infected with 1,000 rabies virions, but it doesn't matter. You're going to have rabies either way. That's intensity-independent pathology. Now, there are a few other terms in our glossary that involve mathematical calculations, so I want to make sure that we talk them through. Let's start with prevalence, and we'll go back to our poor moose. According to Albert Bush and his colleagues, prevalence is the number of hosts infected with one or more individuals of a particular parasite species, divided by the number of hosts examined for that parasite species. In simpler terms, we can say that prevalence is the proportion of hosts that are infected. In our population of 10 moose, let's say that we have 2 that have ticks on them, and the remainder are uninfected. The prevalence of this population would be 2 moose divided by 10 mooses, which is 0.2 or 20%. Average intensity is a different metric. Bush and colleagues define it as the average number of individuals of a particular parasite species among the infected hosts. So intensity doesn't concern itself at all with uninfected hosts. It just looks at those that are infected. In this case, we have 2 ticks on one moose and 4 in another. If we want to get an average, we add 2 and 4, divide by 2, and we wind up with 3. So 3 is our average intensity. On average, each infected moose in this population has 3 ticks. If instead we were interested in the average abundance of parasites, that's a little bit different because when we're talking about abundance rather than intensity, we're taking into account all of the hosts, regardless of their infection status. According to Bush and his colleagues, abundance is the number of individuals of a particular parasite in or on a single host, regardless of whether the host is infected or not. Let's calculate the average abundance of this same moose population. In this case, we add 2 plus 4 plus 8 zeros divided by 10 moose total, which equals 0.6 ticks per host, an average abundance of 0.6 ticks per moose. Now, let's turn to another term in your glossary, aggregation. Aggregation is a property that we can observe in many parasite populations. Let me show you what it looks like. Here's a histogram. As you'll remember from building your glossary, a histogram is a graph that shows a frequency distribution. That is, histogram bars show the number of observations for each bin on the x-axis. Looking at this histogram, we see that the x-axis displays the abundance, or number of parasite individuals per host, and the y-axis is the number of observations of each particular abundance of parasites. In other words, the number of hosts where you observe that abundance of parasites. For example, for 25 hosts, 0 parasites were found. In 15 hosts, 1 parasite was found. The bottom plot shows a regular or normal distribution. Normal distributions or bell curves are rarely observed in populations of parasites. Instead, what we often see is the upper distribution, which is called an aggregated distribution. In an aggregated distribution, the vast majority of hosts have 0 parasites, and then there are just a couple of hosts that have really heavy parasite burdens. This is classic in parasitology. We find it all the time, and it can be for a variety of reasons. Some host individuals make great resources for parasites. Some host individuals have low immune competence, and therefore a low ability to resist infection. And some host individuals engage in risky behavior. All of these things can make just a small proportion of the host population support the majority of its parasites. Nice work building your parasite vocabulary. You're going to want to make sure to refer back to the glossary that you built as you move forward in our video series. I'll see you in the next video.